In this video, I want to take a look at calculating volumes of solids that are generated by revolution, in particular ones that have holes in the middle. So the situation is this. We've got a region in the plane here bounded above by some curve y equals f of x and bounded below by some curve y equals g of x. Now I'm drawing these both above the x-axis to illustrate what I need to do. And then if they're not above the x-axis, then we've got to be really kind of careful. So we'll assume they're positive functions here. The idea is we're going to rotate this around the x-axis, this region around the x-axis. So I always pick curves that are a little tricky to mirror. So this curve would rotate around to generate actually a hole in the middle, and the outside curve rotates around. Let me try a little better on that one. To generate the outside of the solid. So there's a hole that's drilled right through the middle. It's like a donut. Now, just looking at that, I could say, hey, we just did the disk method. And I could look at the whole thing and say, hey, I know the volume inside of that whole thing is the integral from a to b of pi times the function f of x squared dx. That's a pi times a radius squared, where the radius for each value of x, the radius is just whatever the function value is there. Okay. Then I could say, but I don't want the volume. I mean, that counts all the volume, including the stuff that's in this hole, but so I need to subtract out the hole. Well, the hole is just the integral of pi times g squared. Dx from a to b. And that's absolutely right. I want to look at this in a slightly different fashion, though, because it's going to lend itself to other things that we're going to do in later chapters. So I'm going to grab another color here and say, I want to think of this in terms of little rectangles. That is, for each value of x between a and b, I want to draw a little rectangle here. Top of the rectangle is determined by y equals f of x. The bottom of the rectangle is y equals g of x. So the area of that little rectangle, well, let's say the height of that little rectangle, the height here is the difference between the y value there and the y value here. So the y value on the top is f of x, and the y value on the bottom, what's happening? Why is this doing this to me? Is somehow my pencil got deselected. There we go. G of x. The width of that little rectangle is just a tiny little thickness in the x direction. Maybe it's delta x. Maybe it's on the very small. We're going to take a limit anyway as we cut this up into more and more really small pieces. We're going to call that dx. That rectangle now is going to be rotated around to generate an object, and it's going to be what we call a washer. Right? This is going to be a washer. It's a big hole with a smaller hole in it. Actually, sometimes it's called an annulus. Actually, the flat thing I would call an annulus. And then as soon as you give it a little thickness, that annulus turns into what I would call a washer. Not a washer in a wash your clothes kind of sense, but a washer in a put a screw through it and use that to hold the screw head out from sinking into whatever you're screwing into. Right? And so we then calculate the area of this washer, multiply it by dx to be a little bit of thickness, and add those up to get the volume of the whole thing. So it's a different way of thinking of it than what we have here. Let me write this down. The area of that washer is going to be the area of the outside So pi times, well, the outside radius is again f of x. So for each value of x, what's the radius to the far outside? Well, it would be the y value here minus the y value there. Well, the y value at the bottom is 0, so it's just the y value at the top. That's f of x. Pi times that radius squared. Then I want to subtract out the area of the circle in the middle. Well, the area of the circle in the middle is just pi times whatever that little radius is. Well, the little radius is just the distance out between the x-axis and that inside curve. Well, that's the y value here minus the y value there. This one's 0, so it's just g. Then give all of that a little bit of thickness and add them all up for all the values of x that you're interested in. I want one of these things for every value of x between a and b. So this is going to be the volume. This is actually the same as that one because both integrals are from a to b here, a to b, a to b. So you could combine them into one, and you could pull the pi inside of each one of them, and you'd have exactly this integral right here. It is the same thing, thinking of it either way. I like this way, though, just because I'm thinking in terms of area of a slice times the thickness. Add them all up. I want to rewrite this one more time, and I just want to factor the pi out. This would be pi times the integral from a to b of f of x squared minus g of x squared dx. Okay. This is volume by the washer method. Really, it's just a disk method minus another disk method, but we decided to call it washers. Let's do an example. I think I've got an example described down here. I want to start with this region right here in the xy plane. This is one of my favorite regions. You look at the line y equals x, this line right through here, and y equals x squared, which is this parabola. And the area bounded in by those two curves is this region in here. So, what do you call it? Banana? Kind of, well, it's kind of a straight banana. Anyway, that region, I want to rotate this around the x-axis. So the line is going to rotate around to make a cone, and the curve is going to rotate around to make kind of more of a trumpet flare. Now again, I'm drawing this on the plane. You're viewing it on a computer screen. I'm trying to actually draw a 3D thing. This should come up out of the computer screen at you, back down, hit the computer screen right there, and then go behind the computer screen there, come back up. It's just a little tricky to draw. Okay. However, I do have computer graphics that will help me out here, so I'm going to see if I can pull up a computer graphic. So I have here in 3D, he says, the xy plane is here, and the z-axis is kind of coming out at you. The y equals x squared is this line, this curve, y equals x is that one, and I'm going to take little rectangles. Let me show you a rectangle, I hope. There's a rectangle, and I have a slider that allows me to move that rectangle anywhere in the range from 0 to 1, although everything seems to be real slow at the moment, and it's not keeping up with me. This is a real pain in the neck, but anyway, there's a different rectangle. Then I'm going to rotate this region around the x-axis. So again, let me see if this will do this. For some reason, this is really, really slow. I don't know why it's not rotating here. Okay, it's partially rotated. Let me change the angle on it a little so you can see it, that it's rotating around the x-axis there. So the rectangle is being rotated into this red thing, and the curves are generating the solid all together. So here we go, rotate around a little more, a little more, A little more. What's going on? It's like as soon as I hit record, this thing gets really slow. But here it is, all the way rotated around. It should update the resolution here. There you go, nice and smooth. Okay. And you can see that disk, you can see the inside of the disk here and the outside. That's what's generating all of this solid. Each different value of x gives me another washer. Right? You can see I've got this drawn so that the cone on the outside is semi-transparent, so you can see into the inside. So you can see that washer in there. You can see the parabola generating the inside part. Each different value of x gives me a different washer, so I can slide that washer around a bit and see all the different ones. I want to calculate the volume, so here we go. I'll switch back over to here, and I'm going to do the volume is the pi times the integral from the lowest x value I'm interested is 0, and the biggest x value is 1. The outside radius, so for each value of x, I've got one of these little rectangles. The outside radius is y equals x, so I need that outside radius squared, and then I need the inside radius. Well, the inside radius is the distance up to the inside curve here, and that's just x squared. So that's x squared dx. So I need the integral. I need pi times the integral from 0 to 1 of x squared minus x to the 4th dx. This is something that I can probably do by hand, so I will. Pi times x cubed over 3 minus x to the 5th over 5. All of that evaluated between 0 and 1, which is pi. Things are jumping around on me here. Let me see what's actually written on the screen. This is pi times. You plug a 1 in, so that'd be 1/3 minus 1/5. You plug a 0 in, that would be 0 minus 0, for a grand total of pi times, this is 5/15 minus 3/15, so that's 2/15, which you might write as 2 pi divided by 15. Okay. To find the volume of revolution, in the way we're doing it, you're looking at washers. Find the area of the whole circle, and then find, why is this being so weird to me? Sorry. Find the area of the whole circle, and then subtract out the area of the circular hole.